So finally, we're going to go through a number of more specific reactions dealing with aldehydes and ketones. Now, again, in almost every case, it doesn't matter whether we look at the reaction for an aldehyde or ketone. The reaction will be exactly the same. But we're going to start with hydration, which, as the name suggests, is the addition of water. So we'll just put these as R groups again to show it doesn't matter whether we're talking about an aldehyde or ketone. This reaction can be, is done with water, of course, and can be done with either acid or base. And as a result, the product that can be formed is known as the hydrate. And we'll look at the mechanism in a minute. But due especially to sterics, it turns out the hydrate isn't very stable. And for most aldehydes and ketones, we have a preference of approximately 99-1 for it reverting back to the starting material. But as we'll see in a few minutes, there are some specific situations where this reaction not only works, but is fairly important. So let's look at the mechanism. And with this mechanism, we'll consider it both under acidic as well as basic conditions. So under acidic conditions, as we saw before, first step is protonation of the carbonyl. And again, this step happens because under acidic conditions, we don't have good nucleophiles. And so by adding that hydrogen, we make our electrophile, the carbonyl, better. From here, water can attack. And then we lose a proton to get to the product. So that's the mechanism under acidic conditions. How about under basic conditions? Well, it's going to be similar under basic conditions. But the main difference is the order of the steps. So under basic conditions, we don't have water as the nucleophile. We have the stronger hydroxide. And so because we're dealing with hydroxide instead of water, we don't need to activate the carbonyl as we did under acidic conditions. So the hydroxide will just attack the carbonyl itself, and then that O- can pick up a hydrogen. Getting us to the same product. Now, as we said, this reaction is generally not favorable, and only under very specific conditions do we see this reaction working well. But we've actually already seen a good example of that. In fact, we saw it in the alcohol chapter. So if you recall this oxidation, the primary alcohol using Jones reagent. And that would oxidize our alcohol to give us an aldehyde. But if you recall, the reaction didn't stop at this point. if we had started with a primary alcohol, that aldehyde would continue to get oxidized all the way to carboxylic acid. And it's because of this hydrate formation that this occurs. So remember, this Jones oxidation is taking place under strongly acidic conditions. We have sulfuric acid present. So sulfuric acid can react with the aldehyde to form the hydrate. Now, the equilibrium here is not favorable. And we get a very small amount of the hydrate, but mostly the aldehyde. What happens, though, is any amount of that hydrate that does form, it will get oxidized to form the carboxylic acid. And so what we're doing here is basically taking advantage of Le Chatelier's principle in that, even if only 1% of the hydrate forms, that little bit of the hydrate forms, it gets oxidized. And that means then we push that equilibrium a little bit to the right and we form more of the hydrate. Again, that gets oxidized, and eventually over time we end up with full oxidation to the carboxylic acid. So while under most circumstances hydrate formation is not a terribly important reaction, in certain situations like this one, it can be and is a very, very useful reaction. Now, what about the 1,4 addition? So if we're adding water, can that happen 1,4? And the answer is yes. We've said before that hydroxide is not a good leaving group, but being a good leaving group is not a requirement here. It just needs to be good enough. And hydroxide turns out is good enough and will revert back to the starting material. So the 1,4 addition will look something like this. We'll just look at it under basic conditions. But we can see here hydroxide attacks the alkene, pi electrons shift up, and the carbonyl electrons shift onto the oxygen. And then we pick up a proton to get to the product. Now, just like the 1,2 addition of water, the 1,4 addition is still highly reversible and still favors the starting material. But again, there are some very specific, very important reactions where this takes place. And perhaps, the most important might be this one. Now, this one is not an aldehyde or ketone exactly, it's a carboxylate salt. But you can still see that we have an alkene that's conjugated into a carbonyl. And so if we add hydroxide in here, we could get a 1,4 addition. And in this case, it's more correct to say we're adding water, but same basic idea. And we get addition of OH in a 1,4 way. Why is this important? Well, this reaction starts with cis aconitate and forms isocitrate based on a 1,4 addition of water. And this is, of course, one of the steps that we find in the citric acid cycle. Another common nucleophile that we can see added to carbonyls is the addition of HCN. Now, no one ever does this reaction using HCN because HCN, hydrogen cyanide, highly poisonous. And so for safety reasons, instead, you use KCN. But you can only do it under basic conditions, because if you try and do this under acidic conditions and you add water to potassium cyanide, then you'll just form hydrogen cyanide, and that defeats the purpose of trying to do it more safely. This reaction can take place both 1,2 and 1,4. It turns out that CN is a good enough leaving group to be reversible. The 1,2 looks like this. It's the exact same mechanism as adding water, just a different nucleophile. And that's what, with the exception of amines in this chapter, that's what we're going to see, is that these 1,2 mechanisms are going to look the same over and over and over again. And then it protonates to form the product. Same thing, 1,4 addition is possible as well. And again, this mechanism looks exactly the same as when we added water. So nitriles are something we haven't really talked about yet in this course. We'll actually talk about them in more detail in the next chapter. But the main purpose of nitriles is that it's really easy to convert nitriles to a number of other functional groups, including ketones, carboxylic acids, and amines. And so by adding a nitrile, we have another way. And remember, we don't have a lot of ways to do this yet, but we have another way to form a carbon-carbon bond. And then we can easily convert that nitrile into a number of other different functional groups. All right, so where might we run into this reaction? Well, here's kind of an interesting application of this reaction. And it has to do with this species, Aphiloria corrugata, which is a millipede. All right, so what does 1,2 and what does addition of nitriles have to do with millipedes? Well, very simply, this millipede actually stores this compound here. You may recall that that was actually the product of the addition of the nitrile group to benzaldehyde. And this type of compound, we didn't name it, but this is known as a cyanohydrin. And so this millipede stores the cyanohydrin. But when it gets attacked, it actually reverses the 1,2 addition and reforms benzaldehyde. And more importantly, it's how it defends itself. It also releases hydrogen cyanide. So it's the reverse of the nitrile addition, but the exact same reaction.